there was an announcement that we need a new protocol in 1997. This announcement was made by NIST and said we will call it the AES project, and they gave out the specifications of the algorithm they're looking for. It should be symmetric block cipher. It should be adaptable to multiple key lengths. It should be executable in hardware and software and freely available. Many people submitted proposals for this competition. In October of 2000, NIST announced that the winning submission is called the Rindal, which is actually the current algorithm for the AES project. So this is just to tell you that cryptographers did also get things wrong, because in fact, most of the submissions to this call in 1997 were crypt-analyzed when they were made public afterwards. And these were submissions for the new secure encryption algorithm. So AES was standardized in 2002, and it can run in 3 modes, with a 128-bit key, 192-bit key, or a 256-bit key. Although there are 3 different key sizes, the block size is always fixed. It's 128-bit. The difference in the key size decides how many rounds will be ran into this process. So if it's a 128-bit key, then the encryption runs using 10 rounds. And you now know what a round is. A round is this like one box that we talked about in 3D and in DES. This one box that has the expansion permutations and S boxes and all that kind of thing. If you use a 192-bit key, then AES runs 12 times. And if you use 256-bit key, then it runs 14 times. What happens in these times, each one of this 10, 12, or 14 times, what happens is this part. It's something called substitute bytes, mixed columns, shift rows, add round key. It's very similar to the expansions, permutations, and all that kind of thing that was happening in 3DS, but it's a different algorithm. Now, you should realize, why did we look in the details of SDS? Because simply if you look in the details of AES, it's too much. It's too hard. So this is why we looked at the simple one, and now it's up to your imagination to understand or realize how does it look inside the AES itself. So this is one round. This here is one round. As we said, it has substitution bytes, shift row, mixed columns, add round key. Similar to DES, the main key is used to generate subkeys, and each subkey is used in one of the rounds. Again, this is the encryption process, this is the decryption process, and this is just half of it. When we go to the next slide, you will see the remaining part until you reach round 10, and after round 10, it's the ciphertext. If you take the ciphertext, you do the same thing again, but apply the keys in reverse order, and that's the decryption. This is why symmetric key encryption is very nice, because it's the same algorithm. Encryption and decryption also only differs in the order of applying the subkeys. You want to take a look in one AES round, this is what it looks like. So the substitute bytes is these boxes, and each one of them is different, I believe. Shift rows takes a whole row and move it another place. And there's mixed columns, there's matrices in there where you mix the columns in these matrices. And then there's an XOR operation that happens when you do round the key. So you can see the mixed column has some sort of a matrix here. The substitute bytes uses an S box, similar to the one that we looked at, but it's much bigger and much more complex. For you, this looks like very complex, right? But actually, it's easy for machines because it relies on XOR operations, byte shifting, things happen on the byte level, matrix multiplication is carried out on bytes. There is no hard multiplications or factoring or anything like that. This is why, although it looks hard for human beings, it is very efficient for machines, even with 8-bit processors. Now we have like 16-bit and 32-bit and 64-bit processors, so it's even much more efficient. But it's very efficient even on 8-bit processor, which can be very small devices like IoT devices and things like that. So talking about the security is also related to the key size here. Even the smallest key size has a humongous amount of years required to brute force the key. Up until today, there are no known practical attacks on it, neither brute force nor cryptanalysis. There are always people trying to cryptanalyze it, but no one has ever ran successful cryptanalysis on the full 10 rounds of 128-bit key size. It's in use today. It is more efficient than 3DS. It's faster. It's more secure. So AES is the standard that the US goes with alongside with a lot of other countries. So going back to this question, this one is going to appear on exam 2. Going back to that question that was asked on the beginning of semester survey. In general, the security of network communication mainly depends on. We marked these out sometime before, and now we have these 3 remaining. Which one should be the correct answer? The length of the key. Yes. This is the correct answer. So just as a fun fact, I met someone in 2019 at a security conference who thought that 3DS is faster and more efficient than AES. This was something after the conference. We were having dinner someplace and we were talking about encryption and someone said that. So I immediately said, I've got to use this in my notes just to tell students that this is essential information that everyone should know, especially if they're gonna work with any kind of encryption sometime in their lives.